So let's pick back up right there. I've tried to organize a little bit in between videos here. So, again, we're typically concerned about this quantity called the pressure loss due to viscosity, but we might also be interested in the energy loss, or what we call the head loss. Now again, my tablet's not displaying all of those equations there, so let's write these out. The pressure loss, this is page number 4, try to stay organized here. The pressure loss for viscous flow is going to be a friction factor, an F value. This is the Darcy friction factor. We talked about this a little bit in class at the very end of chapter 7 there. So the Darcy friction factor times this quantity we call the relative length, that's length of the pipe that we're flowing fluid through, divided by the diameter of the pipe, times the density of the fluid, and then the kinetic energy, the average speed squared divided by 2. Now again, this F value is what we call that's named for individuals, so let's use capital D. This is the Darcy friction factor. I am not familiar with Darcy. You'd have to go. I can't give you cool stories about him. I don't know much about him, but we name this dimensionless quantity the F value for Darcy. It is a function of the Reynolds number and a quantity we call the relative roughness of the conduit. This epsilon value, that would be epsilon is the roughness, if you will. How smooth or not smooth is the pipe. And that's just a quantity we look up in a table. Right? That's a quantity we look up in a table. And we measure it. And some more about that as we go along. But so we can find the pressure loss. We've got, we're going to talk about how do we find this friction factor, the Darcy friction factor, in just a little bit. So to find the pressure loss, we need to find this friction factor, multiply by the length divided by diameter, multiply by density, and then multiply by the kinetic energy. And we can also find this in other forms. We can find what we call the head loss. Right, the head loss is where we're measuring energy in units of length. And so the head loss, which is really just the energy loss divided by gravity, that's going to be, again, this Darcy friction factor times L over D times the average speed of the fluid squared divided by 2 divided by G. And then we can have what we call the energy loss, or the energy per unit mass loss. Well, that's pretty easy. You can guess what that is. That's the energy loss is equal to, again, this Darcy friction factor times length over diameter times the average kinetic energy per unit mass, V squared over 2. So same exact quantity, we're just measuring it differently, and all we've done, notice, here I'm multiplying by density, here I'm dividing by gravity, here I'm not doing anything to it. This is the energy. So if I take the energy and divide by gravity, I get the head. If I take the energy multiplied by density, I get the pressure. We saw that earlier. Okay, that hasn't changed. It's the same Darcy friction factor, which is going to be based off of our particular fluid, which is the Reynolds number and the roughness of the pipe that's flowing through it. Okay? All right, what else we got here? As we mentioned, what we're really trying to say is I go back, right? Where is it? Number 2. All right, I'm sorry. Here we go. We said completely filled conduits. The loss, our goal here, is to describe the effects of viscous flow. And so, well, for completely filled conduits, that viscous flow is going to be a function of whether it's laminar or turbulent. We use the Reynolds number to predict whether it's laminar or turbulent. Okay? Now once, what we can do with that then, knowing whether it's laminar or turbulent, we can figure out the friction factor based on whether it's laminar or turbulent. This is the friction factor. Right? The friction factor, that laminar, if it's the flow is laminar, right? If the flow is laminar, the friction factor is going to be some constant quantity for laminar flow. The Darcy friction factor is going to be some constant divided by the Reynolds number. And that's where this constant is a function of the pipe geometry. Okay. K is equal to 64 for circular pipes. Okay. You'll have to look up in your text. Now, I've written here page 348. I don't remember which edition of the Chamberlain and Symbolotext that is, whether that's the second or the third edition. But if you look in Chapter 8, you will find a table where it talks about the friction factor for laminar flow. And again, we said laminar flow is if I've got a Reynolds number less than 2300, I can pretty well expect to have laminar flow. If I have a Reynolds number greater than that, probably going to be turbulent. If it's over 4,000, almost guaranteed to be turbulent. Right? So that's how we find this friction factor. It's actually real easy to find this friction factor if I'm dealing with laminar flow. Now, it's not too difficult if I'm dealing with turbulent flow. Okay? The hardcore way to figure out if I'm dealing with turbulent flow, the hardcore way to figure out that friction factor, now this is an F. I don't know why it's not showing it. This is what we call the Colebrook Equation. That is 1 over the square root of F is equal to this minus 2 log epsilon over D divided by 3.7 plus 2.51 over the Reynolds number times the square root of F again. That's the Colebrook Equation. Now, the challenge with that is there's no way to solve this expression for F. It shows up here, and it shows up here. The best we can do is guess and check. So if I plug in a value for F here, and normally I can start with 1 as a best guess, and that's a terrible guess, but I can start out with 1, compute what the F value is based on my Reynolds number and my epsilon over D, compute a new F, take this value, plug it in here again, compute a new F, and just repeat until I start getting the same F value over and over again. It's not hard if you program it in your calculator correctly. Most of the time we're just going to write a computer program to do this for us, or a computer program that already does it, or we're going to use another method. And you can do this on a test, although I suggest one of these other methods. There's what we call the Holland Approximation. Now, I don't really like just getting the first value of F out of the Holland Approximation and going with it. You can, but we'll talk about that when we actually start talking about solving problems. But it's a really good starting place. A lot of times if you take this value F from the Holland Approximation, because you can solve for it here, right? Because if you know epsilon and you know the Reynolds number, you can find this F value, take this, plug it into the Colebrook, and then this value you get here, you don't have to guess and check several times. Just take this, plug it in here, solve for F, done. Okay? Or here's what we call the Moody Diagram. And I've shown you this in class already. Right? For your Reynolds number, different values is a logarithmic scale is normally how this is displayed. So different Reynolds numbers and different epsilon over D's, you find where your Reynolds number matches your epsilon over D, come back over and pull an F value off that. And so this Notice this is Reynolds numbers greater than about somewhere in this 2,000 to 4,000 range. Right in here, you start taking on these shapes. Prior to that, this is the 64 over Reynolds number, or constant over Reynolds number. This is the laminar region. This is the turbulent region. And at this point, then it becomes a function of this epsilon over d. Reynolds number, find where the two intersect, come over and get your F value. Plug that back into here, here, or here, and that gives you your loss term that you can then solve for. That's a good stopping place. I'm going to stop there.